Hello, I'm Rob de Jeu from the Vrije Universiteit Amsterdam. I work in algebraic K-theory, arithmetic, some algebraic geometry in terms of algebraic cycles. And today I'll be telling you about tensor products. So there will be two sections. The first will be basic definitions, and the second will be some basic properties. Tensor products are quite a substantial subject, so there could be a lot, one could say a lot more. And also, unfortunately, maybe a little bit difficult to motivate because the construction looks very abstract, some kind of a bizarre product. But through the lectures, hopefully, with some of the applications, you'll get some idea why one would have to do this. Okay, so I based myself on sections 1.2 and 1.3 of the lecture notes of Ike Moerdijk that are on the ELO website. And if you want more details, because those lecture notes are maybe a little terse, there are many places you can look. For example, in section 10.4 of a book, an undergraduate text in algebra that I rather like, Abstract Algebra, 3rd edition by Dummett and Foot. Okay, so let me has a convention. R will always be a ring. And we always assume that it's a 1, that it has a 1. And so we start with section 1, the definitions. Okay, so in Arno Kretz' talk, he talked about left modules mostly. So the ring R is going to work on a module on the left A. So this will be a left R module. But also, if you let the ring R act on the right, you get what's called the right R module. And the theory is very similar, but as Arno pointed out, the crucial thing is that if you have a product in the ring, R acts on an element in the module, then it's either the first or the second one that sort of acts first. So that's the difference. And tensor products naturally combine a left R module with a right R module. So let me start by making a little correction here for my lecture notes. So A will be a right R module and B a left R module. And then we have as a definition for the tensor product the following. So A tensored over R with B, so this is going to be some big quotient, so let me write it on a separate line. I start with a free abelian group on the set A cross B, Cartesian product. So elements are finite formal sums of elements in A cross B with a coefficient in Z for each one, mostly 0. And we're going to quotient this out by a subgroup generated by, indicated by those angled parentheses, 3 types of relations, 3 types of elements. So if I have A plus A prime in the first coordinate and then B in the second, then in the quotient I want to be able to work out a sum. So I impose that A plus A prime comma B is going to be the same as A comma B plus A prime comma B. And so this is for all A and A prime in A and B in B. Now you want to do something similar in the second position. So A, B plus B prime minus A comma B minus A comma B prime are for all A in A and B in B prime. And so that's the second type.
Can I interrupt for a moment?
Yes.
I think yesterday the notation for the free abelian group on A times B was Z to the power A times B between parentheses.
Okay.
And so maybe you can, so it is Z to the A times B between parentheses, right? To distinguish it from the
Yeah,
product.
I'm not sure why we need parentheses, but now have we write parentheses there.
And so this is the functions from A times B to Z with finite support, right?
Oh, that's the parentheses presumably.
What?
That's the parentheses.
Yes.
Okay. Fine.
And then the elements that are written here, they correspond to the delta functions.
Yes,
Right?
so this
That's
is being
how you-
1 times
Yeah.
the one you usually
Yeah.
leave out. So
Yeah.
this is 1 times AB for it.
Yeah.
For the function that only has value 1 and A, comma B and
Yeah.
0 elsewhere.
Good, okay.
Okay. Anyway, so there's a tool sort of making, imposing some additive relations in the first and the second position, but of course the ring R is at the moment nowhere to be seen, but it does play a role, and it's in the third one. So A was a right R module, so I can multiply an element little a, capital A, by an element R in the right, and then take an element B in the second position, and now I want to be able to move the R across the comma in the quotient, so I'm going to impose that is going to be this one. So this for all A and A, B and B, and R on the ring R. And that's the third type of relation. Okay, and here it's really important to get your left and your right modules straightened out, because otherwise you'll run into trouble with this third relation. So this is called, in words, the tensor product of A and B over R. So it's not so easy to see what it looks like. So we see some examples later on. We first introduce some notation. Okay, so you write A tensor B for elements A and B, and now without the R normally, for the class of A, comma B in the quotient. Okay, so this is the class of the element, say A, comma B here, or maybe 1 times A, comma B if you like. And so that means that A tensor RB is generated as, well, I will say Z module, but that's the same as, say, well, in this case, an additive abelian group. Okay, so I'll casually identify Z modules with additively written abelian groups all the time. So this is generated by, well, those elements, those classes, by the elements A tensor B, with A and A, B and B, and then we have relations corresponding to the 3 types there, and I'm not going to say A and A, etc. all the time, that the notation speaks for itself here. So A plus A prime tensor B, well, according to the first relation, I should be able to replace this by the classes of A tensor B plus A prime tensor B. That's the first one. Now I did something similar in the second. A tensor B plus B prime is going to be A tensor B plus A tensor B prime. And the last one tells me that if I have AR tensor B, I can move the R to the other side and get A tensor RB. Okay, so at the moment, you really have to read this as parentheses around the AR, because R is not an A, only A times R is an A, so this makes sense in that case. And, well, so the first two relations almost look like distributivity. Well, they are, but of course in some new situation. And that has a sort of formal consequence, because we can take A and A prime both to be 0. So as a little exercise, show that we have a few properties, namely the 0, and in order to keep the notation a little bit clean, I'm not going to write 0 sub A, which I should be writing, but it should be clear from the notation. If I write 0 tensor B, then this 0 is 0 of A. That is going to be the 0 of the tensor product. So this class is trivial. And the same thing holds if I put the 0 of B in the second position and the element in the first. So this is a trivial element, or the trivial element in the quotient. And then similarly, you can see that if I take minus A tensor B, for the inverse on the relation in the module A, this is going to be the inverse of the tensor product of A tensor B. And similarly, if I put the minus in the B component. Okay, so it is not so easy to see what this looks like. So let me give you a few examples. The first one is if I take A and then tensor it over R with R, so maybe I should say something about this. R is an additive leading group, and I can left multiply by an element in R, and that makes R into a left module. In fact, if I take any ideal in R, then any sub-module of R is exactly a left ideal if I see this as a left R module. And similarly, I can multiply it on the right, and it will become a right R module, and then a right submodule is exactly a right ideal. So anyway, I can view this. So A has to be a right R module, and this is now viewed as a left R module under the natural multiplication. And you can see that this is just isomorphic to A, and well, just as a Z module, because I probably have no more structure on this thing except for the fact that I start with a Z module, I take a quotient and I get the Z module just from the beginning group. And you can check that the maps A tensor R, if I multiply this out, so to say, if I go to A times R, which makes sense because A is a right R module, I can easily check that those relations will all vanish if I carry this out, and therefore it will descend to a map on this quotient. And the other way around, you're going to go A in A, and you map this to A tensor 1. And then it's up to you to check that indeed that those maps are homomorphisms and they're each other's inverse. Well, so I should first say that they're well defined. At least one of them is required to check, but I indicated it should be straightforward. They're homomorphisms and they're inverse to each other. Well, that is what happens if you put the R on the right in the tensor product, so it's viewed as a left R module. But as I said here, R is both the left R module and the right R module. So I could also put it in the first position and then tensor it with the left R module B. So here this R is as a right R module. And well, this will be isomorphic to B as Z module. And well, so also by multiplying out, so let me just say by similar maps. It's a good exercise to do this, and it's a little bit annoying to get used to using the tensor relations, etc. Those are cool. Those are three kinds of relations, are the tensor relations, and it's very good exercise actually to just do those very simple manipulations that are required here to really let you understand, for example, why exactly one has the left arm module and the right arm module. So it's very instructive to work out those examples. Okay, so let me give you maybe more interesting example. Because of course, if I wanted to write down A and B, I could have done it directly, and there's no need to use a tensor product. So in some sense, this is a pathology. But suppose I take m and n integers with the greatest common divisor of m and n to be 1. Okay, so suppose that I take the abelian group z modulo mz. It's an abelian group, so it's a z module. And z is abelian, so we can be rather careless about left or right, etc. I mean, normally if you multiply this by an integer 3 or something like this, you put it on the left. But if you multiply it on the right, you get the same thing. So it's both the left and the right module, or a z module. And I tensor this over z with similarly abelian group z module nz. U is a right z module. And well, this has m elements, m at least, of absolute value of m. It doesn't say anything about what m and n are. And similarly here, but it turns out that under this condition, this whole thing collapses and it's trivial. So why is this? Well, let's simply take one of those classes A tensor B that we had before, because this tensor product is generated by, well, the elements A tensor B with A in the first one and Z modulo MZ and B in the second one, Z modulo NZ. So if I take any of those elements, any of the generators, well, not all but in the tensor product. Of course, it may not generate the entire thing, but it will be one of the generators. Well, then we can multiply this by m. Okay, it is an abelian group. What comes out, so I can take m times anything. So m times A tensor B. Maybe we should write it like this. And if you now go back to the first relation, okay, so for example, if I take A equal to A prime, then this will be 2 times A, but this will be 2 times A tensor B. So you can work this out for all the integers. So this will be equal to MA tensor B. Notice I'm quite careful about keeping track of the parentheses where you multiply by m. But anyway, this is now going to be the 0 of z modulo mz. And one of the exercises to show that this is the 0 element in the tensor product. Okay, so that is 0. And I can play the second trick, for the second, I can play the same trick in the second coordinate, and now I multiply by n. And again, from the second tensor relation that is written there, you can check that I can move the n, I could move it in the A, but I prefer to move it into the second position now because that's where I work modulo n. And it's also going to be 0 in the tensor product. Okay, and then because I assumed that the greatest common divisor of m and n was 1, I can take a linear combination using the zoo formula for m and n to show that A tensor B. Okay, so if I then use Bezout's formula, I check that 1 times A tensor B is going to be 0. Okay, so every generator is 0 in this tensor product is automatically 0. So I want to conclude this section with, well, first of all, one exercise in this direction. So generalizing this exercise, show that for m and n in z, if I take this tensor product and you can identify it, it is always isomorphic with z modulo the greatest common divisor of m and n times z. So also, for example, if m or n equals 0, because if m equals 0, this is the z, and then z tensor over z of z model nz will be z model nz. It comes out. Okay. Anyway, it's a good exercise. It's a bit clumsing around maybe to get a map, but it's a good exercise to get used to this. So that is an exercise. And I also had 2 remarks to make. So they're not crucial for the remainder, but I want to make them just to indicate that there are some other things around. So first remark. In my definition, which I erased, I didn't really assume all that much about A and B. But in general, so if A and or B have more structure, so the tensor product tends to have more structure as well. So a bit vague. There are many things you could say. For example, A and B could not only be R modules, they could actually be rings over R, so R algebras. And on the suitable assumption, then the tensor will be an algebra. And there's a lot to be said, which we will not do. I just want to give one example, basically, how this can work out.
But can we say that this follows once we know that this construction is factorial in A and B?
Certain things, yes, but maybe not everything. And apart from that, it can be much easier to write it down explicitly on elements than using factorial properties. So both points are valid. Yeah. Anyway, I just want to indicate that there is a lot more that one can say without saying anything or too much in particular detail. And let me give an example of this. Suppose that S is not a ring. And A is what is called an S R bimodule. So this is not defined, but let me just say what I mean by this. That is, so A is a left S module. A is a right R module. Okay, so we already assumed that A was a right R module. Now we assume that there's not a ring, or maybe the same ring acting on the left, but it should be compatible. So the actions of S and R are, well, they commute. So if I take an element in A, little a, and I can multiply it on the left apparently by an element of S, say SA, and I can multiply it on the right by an element R, capital R. And I could do this in 2 orders. So I can first multiply by S on the left and then on the right by R on the result. And I can also reverse the orders for doing this. So first let R act on the right, S on the left. And these should always be the same. Okay, so as a simple example, sub-example, if I take matrices of size n by n over any ring R, then I can multiply this on the left by, by square m by m matrices. So this is a left module over n and R. And I can also multiply it on the right by n matrices. Okay, and then for those, it's easy to check there is a left respectively right module. And then this here is basically this associativity of matrix multiplication whenever this is defined. So it actually is a binary. Okay, so this is a very natural example where the thing occurs. It's not something bizarre that one cooks up. Anyway, So if you're in the situation, so basically A has an additional multiplication on the left, well, then you can do this on the tensor product as well. Well, if this is all the case, then A tensor R B is a left in S module via, so I have to tell you how I'm going to left multiply an element in the tensor product by an element in the ring S. And I'm going to tell you this on generators. And you multiply S times A tensor B. This is going to be SA tensor B. This notation makes sense because A is in the left S module. And then you have to check that the tensor relations are respected, so because this map has to be well defined, etc. And at that stage you're going to need this one for the third type of tensor relation. Okay, again, if you like, you can check this by sitting down and writing all the details. We're not really going to be using any of this. Okay, we just indicate there's a lot more around. Similarly, if B is a bimodular structure, you can also use that to get more structure. Anyway, that's one thing. And the other one is a remark, what happens if R is commutative. Because if you look in many books, they don't define tensor products of arbitrary rings. They tend to assume that the ring is commutative. And they usually then write down a slightly different construction. So let me give that and tell you what the relation is. So if R is commutative, then we also have that this A tensor R over B, so the construction I've given before here, I can in this case start with an R module. So I'm going to stick to this notation. So this is now the free R module. On A tensor B. And presumably one would also write this as R to the power A cross B in parentheses. Finally supported maps from A plus B to R, which is naturally a left R module by multiplying it on the left. Everything with R, also here, the R coefficient you multiply on the left with R. Well, not like this yet, because I have to quote out some relations. And the first two will be exactly like for the tensor product. So I want to be able to work out an addition in the first coordinate. I'm not going to write for all A and A prime, etc. Then also in the second. And the last one tends to write a little bit differently, because in this case I can multiply an element A comma B, which really stands for 1 times A comma B, with an element in the ring R. Before I couldn't do that because it has Z coefficients. So I can give this thing coefficient R, and then I can basically demand, well, say R is commutative, so we don't distinguish between left and right modules. It's always the same. So I'm going to write the R on the left. So in that case, I can write this as R, A, B. So this is what I before wrote AR, but in this context, people will usually be talking about left R modules, and we'll be having this notation. So this is for all R and R, A and A, B and B, and similarly, I want to be able to move the R into the second position. Okay, so the difference of those two is exactly the relation that I had as a third tensor relation before. Anyway, and now I have to not only take the Bealing group generated by this, but I have to take the R submodule generated by those relations, which I indicate like this. And so let me just indicate what the maps are. So I claimed it was an isomorphism, and the maps are as follows. So I can start in the tensor product on the left, and I map this to the class of AB on the right, or 1 times AB. And if I start on the right, so I write on the generator, I have the class of R AB, where R is an R. And well, I cannot write this on the left for R times A times B because I don't have an R module structure there. What you do is you put the R inside, so you can write this as RA times a B. And well, you have to check that they're well defined and that they are going to be morphisms of R modules. I didn't say this, but I'll write it down. This is actually an isomorphism R module, and that they're then inverses of each other. Okay, because this is obviously an R module, but now because R is commutative, if I have a left R module, I can also view it as a right R module by the same thing basically. And therefore this becomes also by this remark a left R module structure by just well, letting the R act on A if you like. Okay, so this is actually an isomorphism. Of R modules. Okay, again, we're not going to use this in the lectures, but this is what you will quite often see if the ring is commutative. Okay, so I think this may be a good time to break the first section. So the second section will be about some basic properties of tensor products.